So we started with generally talking about weights, and then we specialized to give the example of the trace on BOH. The trace it is something like Lebesgue measure on the rail line. For BOH, the trace is like that, and I think. Let me see what it is. So I think at the end of last time's thing, I told you that I proved the following basic fact about the trace, that if you have if rho is of trace class, so I introduced this notation. C1 is the trace class operators, and we saw that this was a two-sided ideal, the star closed two-sided ideal, and if X is in BOH, then both rho X and X rho are in the trace class, so it makes sense to talk about their trace, and we showed that trace of rho X was equal to trace of X rho. Right? In particular, so like Lebesgue measure, here the good spin-off from this, so corollary is that the same thing, if we take a unitary on H, if we take a unitary operator on H, then you can move the thing on the right to the left, and that your U star will cancel, and you'll just get trace of rho. So it is like translational invariance. It is invariance under all the automorphisms of that group, of that algebra. Okay, then what is the one? And the other thing I wanted to say was, so we have this pairing. If you take a row in C1, or let me put it this way, C1 cross B of H to C, we have a pairing. Right? And this okay, and I recall I had shown you that if you take mod rho, that is, if you take a positive trace class operator, then it is diagonalizable. You can put it in diagonal form, and so trace of what am I trying to say? Okay, and what, no, sorry. What we saw, did I or did I not prove that if you take the trace of a trace class operator, what do you mean by the trace? You take the sum of the diagonal entries with respect to any orthonormal basis, and you will get the same thing. Did I prove that you get the same thing for any orthonormal basis? Okay. So what is this? So this by definition okay. So if mod rho is diagonal alpha I, then trace of rho x the same as trace of x rho, which is trace of x u mod rho, which I can write as, what is this? This is the sum of the II entries of xu times mod rho IA. Right? I deliberately split it like this because mod rho is a diagonal matrix, and I've been trying to make you competent in multiplying matrices by diagonal matrices. So what do you get? This is going to be sum over I of, not sum over IA, sum over I. This is xu ij times alpha j. Right? So multiplying the matrix xu with the diagonal matrix alpha. So the jj entry, sorry. The jj entry of this is going to be xu ij times alpha j. Okay, which is less than or equal to look at each xu ij. Sorry? Summation over? I'm changing the I to j. I'm changing I to j. Sorry, no. No. So what is the II entry of this? II times alpha I. Okay? Anyway, but what is xu II? It is after all xu in a product xi I in a product xi I. So any matrix entry is bounded by the operator norm of that operator. Right? So this is each of these. So if we take absolute value, And what is this? Is the trace of mod rho. Now, see, we define so in general we define the so-called one norm on C1 by trace of mod rho. Okay, why is this a norm and so on? Let us. Why do you have mod of rho plus psi and so on? Are they complicated things? So let me just define it like this. And what you can see from this equation is that mod trace rho x less than or equal to norm x. So this norm is the infinity norm, the operator norm. So I read infinity for operator norm, and one for this is the so-called trace norm. So norm x infinity, norm u times trace mod rho and this I can forget, norm u is less than or equal to 1, right? So less than or equal to So I defined something which I called the one norm without verifying there is a norm. But what I've shown is that I have mapping from C1 to B of H upper star by rho going to exactly trace of rho dot. I'm doing this kind of badly. See, what I'm trying to say is that I'm trying to, in fact, identify C1 with the pre-dual of B of H. So I told you, see what was the pre-dual of B of H? It was the closure of those, see in B of H star, you had these omega psi eta, right? Which were defined by x going to x eta. Right? But now what I'm trying to say is that this is actually okay, so I should apologize in advance because today, for various reasons beyond my control, I haven't prepared two things, so I'm going to kind of ad-lib, so let's hope that I get things right. So, okay, so see, physicists use this notation. See, I think, did I use that Z psi tensor eta bar notation here in class? No, it's okay. Okay, so physicists use the following notation. They define, see, if psi and eta are in the Hilbert space, they write eta to be the element of H star. Right? This is half an inner product. So to complete it, you must put a psi in front. So psi going to psi bracket eta is a continuous linear function. Those are all of them. And so they write elements of H star by this notation and elements of H they denote by this notation. This was Dirac's notation. He called this a bra and he called this a ket. So the whole thing was a bracket. So you put the two together, you get the number, the pairing. Okay, so if you put them this way, then you get a number, a bra times ket. But on the other hand, look, this ket times bra also makes sense. That is, if I take this is an operator from H to H. What does it do? It takes a zeta elements of H are denoted by this, right? So you take a zeta and you put that in here. So zeta goes to you do the only thing you can. Zeta goes to zeta and product eta times psi. Right? Or if you don't like the bra and ket notation, you just think of this as the vector zeta going to the vector zeta and a product eta times psi. Now this is clearly an operator of rank 1. It sends every vector to a multiple of psi. So it is a rank 1 operator, and conversely every rank 1 operator will look like this. If with rank 1, let's say the range is spanned by a vector psi, then any zeta must go to some scalar multiple of psi. That scalar will give you a linear functional from the Hilbert on the Hilbert space. So that will come as inner product with something. So any rank 1 operator can be written like this, where you can in fact choose the psi to have a unit norm.
So what is the definition of this left bracket zeta and then
this is the way they write the inner product. So far I've been writing inner product like this. Physicists, rather than writing a comma in the middle, will write a vertical line.
So I'm saying, sir, the first half, the left bracket zeta and
Element of each.
yes, sir.
So I denote elements of H with this notation.
Notation.
Rather than saying psi and H, I would think of them as bras like this. Okay, so see if you so here a little see, suppose you take a so rank 1 operators look like this, right? So if you multiply such an operator by what do you think we'll get? See, the notation is beautiful. You just collapse the things together to get an inner product in the middle. So the answer will be actually psi 1 eta 2, which is a number, times eta 1 psi 2. You can verify that is exactly how you can compose the two operators. What does this do to a vector zeta? It takes zeta inner product eta 2 zeta it is going the wrong way. No, that's because I'm putting the operators on the right. So sorry, this is not correct. It is see if you start with a vector or I myself am getting confused by this bracket notation. So instead, let me write this as see, I prefer this notation. This is the physicist notation. Rather than this, I will use my notation will be psi tensor eta 1 bar. So just think of it as notation for the moment. Right? We can justify this later. So just think of this. So this is the operator. See, I put a bar here to recall that. See, this is the operator. That this whole thing is going to be conjugate linear in eta and linear in psi. See, this acting on a zeta is going to be zeta eta 1 times psi 1. Exactly what I said earlier is the Brown notation. But except that the reason things went wrong here is that you're putting the operator on the right and the vector on the left to get the answer. In the bracket notation, what do? If you operate this operator on a zeta, that won't quite make, you can't put two kets together. So really the way this thing works is to put the vector at the left and the operator on the right, which is why this multiplication rule went wrong. So I should have put the vector at the front, and if I do that, then you'll be composing the other. See, this is a notational hang-up that everybody has to resolve. See, if you want an operator from V to V, you could call this as an x going to. So we typically use this kind of notation. But the French school will also write this as xt. So typically this is like, if you think of vectors as operators as matrices, and if you think of vectors as row vectors, then you must see the row vector on the left and then the matrix on the right to get a row vector. So this corresponds to thinking of operators as vectors as row vectors, and the linear operator the right multiplication by. So when it is right multiplication, the order will reverse. So anyway, so rather than getting unnecessarily confused by semantics of this kind, let me stick to this notation, because this is pitched to the left side definition. So if you now do C1 tensor eta 1 bar times C2 tensor eta 2 bar and you operate this on a vector zeta. What will you do? At the first stage, you will take inner product of zeta with eta 2. And then out will pop out of psi 2. Then the psi 2 will go an inner product with eta 1. And out will pop up psi 1. So what you see is that in fact this product is equal to See, what does it do to zeta? There's the number psi 2 eta 1, which is outside, and then it is eta psi 1 tensor eta 2 bar. Whereas earlier I was writing the wrong definition because of things I was confusing between right and left. Okay, so why am I going to all this nonsense? So I'm saying, suppose I want, see any, if I take a vector of the form psi tensor eta bar, I'm saying this is of trace class. To say it is of trace class is equivalent to saying that modulus of this is of trace class. That means I will look at this star this. Okay, so what is, so let us do the other computation. So what do you think this will be? Yeah, so I'll just leave it as an exercise. Just sit down and verify this. There is that if you take this zeta inner product, some zeta prime, or do it the other way, then you will get the two things. So the adjoint is obtained by flipping the two. Okay, so if you take mod psi tensor eta bar squared, that is this star this. And this is eta tensor psi bar times psi tensor eta bar. And what is this? We wrote down the rule for multiplication. You take the inner product of the middle two fellows, right? Observing which is linear and which is conjugate linear. So here the middle two are just psi and psi bar. So this is just going to be norm psi squared times eta tensor eta bar. Okay, so that means mod psi tensor eta bar. So I want a positive operator whose square is this operator. Assume for the moment that eta is rank 1, is norm 1. If eta has norm 1, then what is eta tensor eta bar? It is just the projection onto the one-dimensional space spanned by eta. As I'm saying. Anyway, what is eta tensor eta bar squared? You can see that. There is I'm putting psi equal to eta in this. If you take eta tensor eta bar squared, you get norm eta squared times eta tensor eta bar. right? So, uh, I want to find the positive square. So let me make things easy on myself. Let me assume, suppose norm psi equal to norm eta equals 1. Then your multiplication rule will tell you that modulus of psi tensor eta bar squared equals eta tensor eta bar. Which, in the same thing, if you put psi equal to eta tensor eta bar is self-adjoint. Right? So this is also equal to eta tensor eta bar squared. Consequently, eta tensor eta bar, as we just saw, is the projection onto the span of eta. That is exactly what the projection will do. Take inner product with eta and spit out the eta, that multiple of eta. Okay, so this is positive, and so that means the positive square root of this thing and what is this? This is a rank 1 operator. See, so here, so there is the assumption that eta and psi were unit vectors. Otherwise, you must scale it up by some constant. So assume to start with that psi and eta are unit vectors. Then, what is trace of eta tensor eta bar? How do you compute this trace? Then you will, yeah? Inner product? But why? Norm of eta is 1, okay.
So, take extension of eta.
You take eta and extend that to an orthonormal basis. And write down what eta tensor eta bar does to that orthonormal basis. What will it do to an eta n? For n equal to 1, it will give you back eta. For every other n, it will give you 0. That means as a matrix, eta tensor eta bar will have just a 1 as the 1, 1 entry and 0 everywhere else. So the trace of this is just 1. Right? And in fact, in fact, more generally, suppose you have a, see, what is psi tensor eta bar? It is the thing, the operator which if psi and eta have norm 1, it will send eta to psi and it will kill everything orthogonal to eta. Right? More generally, if hang on to letters, what shall I say? Okay, suppose Z has finite rank. That means finite dimensional range. There is so the same will be true of, so what does such a finite rank operator look like? Huh?
Summation of alpha I and rank 1.
You know the answer, you shouldn't say that. No, but we've been studying how to write. We've been studying operator theory through this course. We should know how to figure this out. If Z was a positive operator and it has finite rank, then it lives only on finite dimensions. Then, if I take an orthonormal basis for its range, then for its range there is an orthonormal basis consisting of eigenvectors. That is Spectral theorem for positive operators on finite dimensions. So that means mod Z will look like summation alpha n eta n tensor eta n k equals 1 to n. Suppose it has n-dimensional range, where eta k is an orthonormal basis for the range of mod Z. By just restricting attention to that range, if that range is n-dimensional, so if the rank is n, then the range will have an orthonormal basis of n eigenvectors, and it will be diagonal. You can find a diagonalizing basis of that size. So mod Z will look like this, but this is an orthonormal basis for so that means what is the support of mod Z? The support of some operator means there is a projection onto its range if it's a positive operator. So how do I write, if I know an orthonormal basis for the range, then can I write down what this thing is? This is exactly going to be somebody else. It is just going to be summation eta k times eta k bar any orthonormal, if you take, in fact, for this you don't even need it to be finite. You take any subspace, you want to give a description of the projection onto that subspace, you take an orthonormal basis eta k for that subspace, and the eta k and the eta k bars will all be rank 1 projections. They will be pairwise orthogonal that project onto eta k, and the sum of those is by definition the projection that you started with. So the submode of mod z is spanned by the eta k's. But now, so we've done half the analysis. Now we wanted to understand the operator z. I've told you how we can understand mod z. For mod z, we use the polarity with the spectral theorem. Now, to understand what z looks like, we should now further use polarity composition. That is the passage from positive operators to all operators. And now eta k's are an orthonormal basis for the range of for the submode of mod z. That means if you take the polar decomposition z equals u mod z, then initial space of u is exactly the submode of mod z. Okay. So when I read this as rank n, that means the alpha k's are positive. Those are the eigenvalues. But that means eta k's are an orthonormal basis for the initial space of u. So it will follow that u of eta k's will give you an orthonormal basis for the range of u. So this means if I read psi k equal to u of eta k, then psi k is an orthonormal basis for the final space of u, all the same as saying the range of z. That means what does z look like? Therefore z looks like see, I've spelled out in the tensor notation, I've spelled out what the polar decomposition is. What is u? U is equal to summation k equals 1 to n ck tensor eta k bar. It sends the etas to the xi's. These are orthonormal and these are orthonormal. And mod z is summation alpha k eta k tensor eta k bar. So what is z finally? That is u mod z Right? So you read on sum over k and l. Alpha L Ck tensor eta k bar times Cl tensor eta L bar. No, eta L tensor eta L bar. And what is this product? You must take the inner product of the middle case. So there will be non-zero only for k equal to n. Right? So it will be exactly sum over k, alpha k, psi k tensor eta k bar. So we know what any finite rank operator looks like. Okay. And suppose I want to find what the trace of xz is. So I take any x in B of h. Now z is a finite rank operator. So we prove that each of these ck tensor eta k bars, every site of theta bar is of trace class we saw. Every finite rank operator is certainly of trace class. And so it makes sense to talk about trace of xz. So what is that? You must compute xz zeta n for some orthonormal basis. So how will you choose the orthonormal basis to make this computation easy? Extension of? Because z is going to send the etas to the x's. So if you take the etas and extend them to, if you choose them to extend the etas, then this z, this is what z does. So if you take any eta orthogonal to all the etas, then z will kill that eta. That means z zeta k will be 0 for k bigger than n. I should have written m. So that so what will the final answer be? Summation I equal to 1 to n
x zeta eta.
So let us see what. See, if you take for the first n, what is z zeta n? the first so many zetas are just etas. And the z of an eta is alpha times that xi. Right? So this will be x times alpha is a scalar, so then you can take it out. Psi n eta n. Huh?
Alpha I.
Sorry, alpha I, eta I. That is, this is exactly the pairing of x with summation alpha n I omega psi I eta I. This omega psi eta was the thing which by definition sent an x to this inner product. See, when in the first lecture when we started talking about the pre-dual of B of H, so I said on B of H you have these special functionals omega psi eta, and their linear span was called some f or something, and then f closure was the B of H rho star. And so what I'm trying to say is that so when Z has finite rank, trace of xz looks like this, and what is the one norm of z? So you were saying mod z was this, and what was the trace of mod z? It is just going to be the sum of the alphas. Right? That means so I'm trying to derive this from what we've done before. See, if you look at x going to trace of xz, where z has finite rank, we call this functional phi. Then what we've seen is that what is the norm of this phi as a linear functional. So by what we said earlier, this is smaller than or equal to norm x times the trace norm of Z. We call this functional phi Z. That means the linear functional phi Z on B of H has norm is less than or equal to the one norm. I'm saying actually it is equal to, because see, I can take X to be equal to Z star. Then what is phi Z of X star? It is trace of X star, which is the same as trace of X star X, which is trace of mod X squared, which is summation alpha I squared.
X is equal to U star. U is partial asymmetry plus only
Very good, very good. Let us take X equals U star.
U star Z. U star Z is equal to mod Z.
Trace of Z U star Z, which is trace of mod Z, yes sir, thank you. So this says that, see, and U star has norm 1, operator norm 1. So the operator, therefore, so this is the, that means this value is attained at some point in the unit ball. And if you recall, there was this thing that I don't know if I did that or not. We were trying to show that the extreme points of the unit ball of B of H were partial isometries. That means you take the absolute value of a linear functional, it will be attained at one of the, at a partial isometry by Klein-Milman theorem, and so that is what is being illustrated here. The phi Z attains this norm at U star, and that is exactly equal to it. That means on the, see these phi Z's as Z ranges over all finite rank operators is exactly the span of the omega xi etas. We've shown that every Z is a span of omega xi etas, and conversely every such thing clearly has finite rank. And we've shown that for such finite rank operators, the operator, the norm of the functional associated is nothing but the trace norm of that operator, of that finite rank operator. That means the pre-dual, if you recall, was defined as the closure in the norm of B of H upper star of the span of all omega psi etas. That means the closure in the one norm of the finite rank operators. Which is precisely the class of all finite rank operators. So I'm saying that if you take any finite rank operator, it will have a similar decomposition, but which will be infinite, using that compactness argument that I vaguely quickly went through that last time. That is what I was trying to do. Doing this confused argument one previous time, proving that if you take a trace class operator, a positive trace class operator must be diagonalizable. So that argument that I gave, so using that, one shows that in fact the trace class operators are precisely the closure of the finite rank operators with respect to the trace norm, which was the way we defined that B of H lower star to start with. So I'm saying, so the one norm that I defined as the sum trace of mod rho, that is in fact a norm, and that is a norm as a linear functional on B of H. And so finally the conclusion is B of H lower star is identifiable with trace class operators with a rho going to corresponding to the functional trace of rho dot. The functional that's in the next trace of rho x. That is the functional, and so the okay. So let me quickly end up this discussion of nets today with some not very precise statements, but which I hope you will be able to get something out of, which is okay. So this trace is an example of a weight. Similarly, an infinite measure is an example of a weight on each L infinity space by integration against that measure. See, but weights can be kind of uninteresting. See, here is an example of a weight. Phi of so I will define it for positive elements for x and m plus. Suppose I define, suppose phi of x is 0 if x is 0, which of course it has to be, and suppose I define everything else to be infinite. They like defining a measure and saying that measure of every set is, for the empty set the measure is 0, for every other set the measure is infinite. That is certainly a measure, but it's not a very interesting measure. So one doesn't want to look at such kind of triviality. So one says that a weight phi is, see, for measures, how do you get around this? I can take a measure and define a measure to be infinite for all non-empty sets. So to rule out that kind of uninteresting measures, when you want, what kind of condition do you put on measures?
Mu phi equals to 0. What is it?
No. I want to rule out that trivial case of mu of the empty set is 0, mu of every non-empty set is infinity. So if I want to rule that out, what kind of hypothesis on the measure can rule out such trivialities? Huh? That is finiteness. That is, the measure is finite, you are saying. I want to look at, weights for which phi of 1 is 1 correspond to actually positive functionals. They correspond to, if phi of 1 is 1, they correspond to actually states on that one-dimensional algebra. But if I want to look at infinite things, it is like measures which are, they are not probability measures, they are not even finite measures. They are infinite measures, but they are not trivially infinite. So what kind of condition can you impose on a measure to guarantee that? Come on, yeah, you guys have done a course on measure theory. This
So at least one element in a class such that this is
just one doesn't make sense, no? Oh, okay. So you're saying, let's say you're saying, for example, unit interval has measure 1. Every other set has infinite measure. That doesn't make sense because if we take the interval 0 to half, there will be a subset of 0 to 1. So you can't have infinity smaller than 1. You want some things to be finite, or you want for measures. Come on, you've heard this expression. No, that is the regular thing. So there is no topology. So you just have a measure space. What is the? I want to be able to exhaust the whole space by sets of finite measure. There should be enough finite sets of finite measure. So,
Talking about sigma
the Ramayana stress. Now, like sigma finiteness does it like for measures you say it is sigma finite if the whole space can be written as the union of finite measures, of sets of finite measure, as countable union. So here one imposes something similar, it is called semi-finite. If, so the definition slash theorem. The theorem will say the following are equivalent. So I list a bunch of conditions, then one proves that in fact they are all equivalent, and when they are satisfied by a weight, you call it semi-finite. See, we had that set that is denoted by M phi, which was n star n, right? Which was an algebra. And on these algebras, the weight actually gave you a linear function, gave you a positive linear function. It's a star algebra, and the weight restricted to this is a positive linear function. So, if this is sufficiently big, so in von Neumann algebra, the natural topology is the sigma weak one. Another one. Okay, you take, see notice the following thing. If an x is in that D, if you have something with finite phi value, that means it is positive and it has a finite phi value. Now I want to use functional calculus and notice that I've used this before. If you take, see, from some epsilon to infinity, you look at the function f of t equals t up to there, and then 0 before that. Then we've used the fact that t indicator epsilon infinity of t is greater than or equal to epsilon indicator epsilon infinity. I'm just stating a triviality. On epsilon to infinity, t is bigger than epsilon. But this means this I can also put on the left side, the two things commute. So this means that 1 epsilon infinity x times x is greater than or equal to x1 epsilon infinity. Epsilon times. For any positive x. So now if I choose an x in D, suppose that means x was positive and it had finite phi value. Then what will this equation tell you? See, and x is greater than or equal to this. See, f of t is greater than or equal to t times some indicator function. So x is greater than this, so x is in D. If phi of x was finite, then phi of this must be finite. That means there must be projections in D. There must be projections with finite phi value. So in fact, if you take the centerfold E in P of M, such that phi of E is finite, so to say it is semi-finite means that certainly there exist many such projections. So to say that there are enough such finite things is the same as saying the soup of all these things is one. This is like saying the soup of all sets of finite measure is the whole space. Okay, so rather than getting into a diatribe about these technicalities, so okay, there is one more requirement, one more definition. We say that a weight phi is normal if
So in the 2, is it countably many? Can you find out?
countably many way.
Yeah, whose union is equal to 1. Like that sigma finite measure.
Because we right at the beginning we said we will only restrict ourselves to separable Hilbert space. We are only looking at one-Neumann algebras with, then I'm also saying we are looking at one-Neumann algebras whose pre-dual is separable. So in separable Hilbert space, if you have an uncountable family, see what does this mean? Then by John's lemma there will certainly be a family in here which are pairwise orthogonal whose soup is 1. You take maximal collections of pairwise orthogonal projections in this family, and their soup will be 1 by the same thing. But any such collection must be countable because you are in separable space. Okay, phi is normal if it respects, see exactly as for linear functionals, normality means sigma v continuity. That is the same as saying monotonic convergence. monotone limits. That means phi of soup xi is soup phi xi for all monotone nets xi in M plus. That would be the obvious understanding when something is infinite, then how you deal with the arithmetic of infinity.
Say notes B in class.
No, but here in M plus it is automatic. In D it is in requiring it in M plus and requiring it in D are the same. If you're not in D, that means if one of these guys is infinite, if one of these is infinite, then certainly this is infinite. Because phi respects order. So if one of them is infinity, then the infinity greater than equal to it's only the finite cases which are of interest, where anything sensible is being stated here. So in one-dimensional algebras, when you look at states, then you want to look at normal states. And there is a GNS. Did we discuss GNS at all? Okay, then 1 o'clock is not the right time to talk about GNS. It is a completely fundamental construction, so we'll talk about it. Thank you.